What's amazing is that you can actually see mental imagery. So when you imagine something, you generate activation in these maps that is similar to the activity you'd see if they were seeing or feeling the things. It kind of blows my mind to this day that you can give someone a brain scan and tell when they're imagining a face versus when they're imagining a house.
From the offices of the Weill Cornell Medicine Brain and Spine Center in New York City, this is Your Brain with Dr. Phil Stieg. Internationally renowned scientist and researcher, Dr. Phil Stieg is neurosurgeon-in-chief of the New York Presbyterian Weill Cornell Medical Center. This week, Dr. Stieg and his guest explore maps in your head.
Hello. I'd like to welcome Dr. Rebecca Schwarzlose, cognitive neuroscientist at Washington University School of Medicine. Her recent book, Brainscapes, explains our brain maps and how they are important in our understanding of the world around us and how we as individuals perceive the world through our senses. Becca, thank you for being with us today.
Thank you so much for having me.
So in reading through the book, which I'm fascinated by, and the way that you translated the complex nature of the brain into layperson speak is superb. I just want to understand, you, in the book Brainscapes, describe brain maps. So, Becca, the first question I have to ask is, in your mind, what is a brain map?
So it's a great place to start because I think it's often a very foreign concept for most people who are not in neuroscience that we might have maps in our brain. Brain maps are physical things. They're parts of your brain. They're areas of tissue in your brain that represent certain types of information. They're laid out in a way that reflects reality. So for example, you have a very large visual map at the back of your brain that represents what you're seeing at any given time. And it's laid out in the tissues of your brain, at the back of your brain, according to how the things are physically happening in front of you, so the visual information coming into your eyes. And to give an illustration of what that means, if you were to pierce that map, you would become blind in a part of what you can see, or what we call your visual field. Conversely, if someone were to stimulate a part of this map electrically with an electrode or other techniques that can be done from outside the brain, I could make you see a flash of light that isn't actually there. This map, which is laid out, as I said, according to what you're seeing in your physical tissues of your brain, is representing what you see and really mediating your experience of visual perception.
So the brain map is a specific location within the brain.
Yes.
Like a map.
Exactly. So there's an actual part of the tissues of your brain that are representing a certain thing, and within it, they are organized in their representation according to features of your environment in a map-like fashion.
So then how is that different from everything we read about in Scientific American regarding neural networks?
Yes, so neural networks are referring to the properties of many neurons that are connected and able to send signals to one another. And these neural networks don't rely on the location of where things are in the brain. In fact, when people model them, they just model them sort of arbitrarily. There's no spatial relationship among them. It's very different. It's sort of a representation of information in a distributed fashion.
You suggest that brain maps are essential for our survival. Is that true, and how do they do that?
All creatures with brains have brain maps, and the reason is because it is so advantageous and really kind of crucial for making sure that we can perceive as much as possible of the world that we need to perceive, the features of the world that are crucial for us to survive and not die, and to procreate and make more brains that will have babies and have more brains. But also it allows us to keep our brain size small, which is actually really important because if we had really big hulking brains that we would need to perceive all of the things that we perceive now, we'd have to tote them around. We couldn't hide from predators. We couldn't sneak up on prey. It would be very impractical.
In the book you mentioned brainscapes are the landscape that a brain map predicts. I'm dense. Explain that to me.
So our brain maps represent not all of reality. Our brain maps represent certain facets of reality that we rely upon to survive. But then even within them, they are warped. So in our case, the visual map is warped so that it is over-representing information that comes into the center of our gaze, where we're pointing our eyes. And therefore, we have far better perceptual detail at the place that we're looking than in the periphery of our eyes. When I describe a brainscape, it's a word that I made up to try to describe what is kind of perception as it is mapped by the brain. Because in many senses, that is closer to what we actually experience. We're used to seeing our visual world with greater magnification where we direct our gaze. We don't even think twice about it. But of course, in reality, detail is all around us, and we are just culling out one portion of detail wherever we look.
Well, that was the interesting thing, too. Talk about that process of really focusing the sense and also the magnification that occurs within the brain.
Yes, absolutely. One of the things that I get to relatively early in the book is how actually the physical constraints of our brain really drive the need for our brain to make these maps. That this is part of how our brain saves space and keeps our heads and our brains reasonably sized, and also reduces the amount of caloric intake we have to do to feed this active, hungry brain. So magnification is even kind of beyond that. It's a way of culling out anything that is not absolutely necessary and focusing on specializing and making the most of what you can represent.
So it's a little bit like the computer always getting smaller and more efficient.
Yeah, it is. And I allude to that idea when I talk about this conundrum with brain evolution, that it's a little bit like engineering a device, and you want it to be small and portable and energy efficient. But, in order to do that, you have to think about how it's laid out, and you have to put in pieces that need to talk together, close together.
Unfortunately, we don't have enough time to go through every one of the senses that you review and the brain maps that are involved with vision, hearing, taste, and smell. Let's take vision. You had really good examples of children born with cataracts and how that affected their visual field development. Talk about that.
Yes, absolutely. There's a period during very early life where our brains are highly plastic, highly ready to learn, and the neurons within them can learn to represent different features of our environment. Those physical, sensorial experiences that newborn babies and very young children have are actually teaching their brains how to represent the world around them. And if you have a child who has a major disruption of sensory input, for example, they have cataracts that prevent them from having high frequency visual inputs or like kind of distinct visual inputs, then their brain maps, when it's developing, will not develop in a normal sense. The features of the input have affected the way that the brain map develops. And that can be really problematic because if you don't get those cataracts taken out, or in the case of misaligned eyes, if you don't correct the misalignments, these kinds of visual impairments, even though they're correctable, they can leave long-lasting changes in the brain and have permanent kind of visual impairment, even though you can fix the problem with the eyes.
I really felt that where your concept of brain maps and brainscapes came together was when you were talking about recognition. And you used the clinical examples where John had a stroke in the back part of his brain, his occipital lobe, which is vision, and part of his temporal lobe. And he could describe a carrot and go through all the things, but you put a carrot in front of him, he couldn't name it. And then Terrence apparently had a stroke in another area, and he couldn't recognize a face. What's going on?
Yeah, so my early work was focused on face recognition and object recognition. And I really fell in love with these portions of the brain that are more or less dedicated to recognizing types of things in our environment. To many people, it feels surprising to hear that our brain has, like a chunk of the brain that's kind of dedicated to, for example, recognizing faces. And if you damage this chunk of brain, you will have these severe impairments in recognizing a face. So something that feels effortless becomes impossible. What really this speaks to, and especially these areas, is the importance of experience. There's another area nearby, these zones, that is very specifically helps you to recognize written letters. You only see it develop in individuals who learn to read in childhood. So you can see that experience playing a role, that having that early experience learning to recognize and decode letters creates this focalized zone that helps you to do that ever after.
This kind of gets back to what you were talking about earlier then, right? You want to decrease the size of the brain, so you decrease the amount of energy you need to keep it ticking by improving the efficiency. So you see an object. You don't just see I think many of us think, oh, I see a blue eye. No, you're looking at the whole face and putting that together, and your brain is trained to see that, correct?
Correct. Well, yes, you've learned to do it. And more so than any other type of object in our world, faces are particularly hard and particularly something that we continue to learn. Whereas some of these other zones for object recognition kind of mature very early. They sort of get to a certain size and stay put, and our abilities to recognize other types of objects get pretty good pretty early. But faces, we continue to see changes in this face region well into adolescence, so that as you get older, as you go through high school, say, you're still improving and learning and developing this region and becoming better at doing face recognition, which by all rights is very hard because faces all have all the same parts in the same general configuration. It's really just these fine details and their alignment that helps us get there.
But we throw around the word recognition like it's a trivial matter. I mean, it's important. I mean, what is the difference between vision, seeing something, I see a flash in the sky, and recognizing something? And I think this is important when I start thinking about legal cases and somebody describes and says, I saw that person do it, you know?
Absolutely, right. And I talk about that in the book. The carrot example where you describe, he can describe every detail of the carrot that he's looking at. He can describe the color and he can describe the shape and he can make some educated guesses about what it might be. But that kind of flash of light recognition, which is really based on experience and memory, right? We learn what a carrot is through experience and we remember it. But of course, every carrot looks different. So there's some feature where we have to sort of extrapolate and be able to pick up on these generalized features of the environment and the objects that we experience to later recognize them. And it's just amazing that we do it so effortlessly that it doesn't seem like a separate step. And yet when you hear about patients like John who can see but not recognize, you realize how very different those things are.
Following up on the developmental aspect of it, I was also enlightened when you talked about the different cultural aspects, say, of smell. And you highlighted the difference between Western civilizations, where smell's not so important, and the Jahai civilization, where it's very important. Can you tell us what the Jahai culture is?
So the Jahai are a hunter-gatherer society in the Malay Peninsula. They actively go out and find food in their environment. And therefore, they are using the sense of smell for their vital ability to find edible food and identify edible from poisonous plants. So for them, smell is the difference between life and death. In the example that I gave in the book, they have this very rich kind of language for talking about smell and really just extremely good at identifying smells. And Westerners are horrible at this. We don't have to do much of that in Western society. We go to our grocery store, we open our refrigerator. We don't have to be so discerning with our smell. So we have not been using that sense the way that other cultures may be. I think it's something that we need to be paying far more attention to in the field of neuroscience because we have a tendency to overstudy the available individuals at our disposals. And it's easy to think that that's the norm for humanity, but the truth is that there are so many ways of life across the globe, and those ways of life can really affect how individuals have to use their senses.
Your brain may be compact and incredibly efficient because of its ability to create maps inside your head, but what about the maps outside of your head? Some people were always better at navigating with maps than others. For those who get hopelessly lost, GPS devices that take you to your destination one turn at a time have been a godsend. But what are these systems doing to our brains? About 10 years ago, Amy Lobin at the University of Oregon published a study of how people read maps. Turns out that those who hold a map with north at the top can visualize their position and orientation on the map. Those who rotate the map to match the direction they're facing on the highway activate different brain structures. Lobin believes this ability to mentally rotate images in your head is connected with the parahippocampal area of the brain, close to areas connected with spatial memory and images. But as paper maps become obsolete and we become more and more reliant on the GPS devices in our cars, are we losing the ability to sense where we are?
Turn left after after a quarter of a mile onto I-678 south toward Kennedy Airport.
In a recent study, researchers at McGill University examined the effect of GPS use on people's brains.
Turn right after 400 feet, then turn left immediately.
They found that getting step-by-step directions from GPS activates yet another region of the brain than used when we're looking at a paper map. And using GPS may actually suppress our spatial memory skills.
Turn left after 800 feet onto I-678 south.
The study showed that the more someone used GPS over a 3-year period, the steeper their declines in spatial memory, among other skills.
Turn right after 400 feet.
Take away GPS from people who have grown reliant on it, and they show a significant decline in their ability to navigate the old-fashioned way. Many participants reported that their trust in their sense of direction had declined the more they used the GPS. Perhaps map reading is becoming a lost art and may someday be as rare an occurrence as men actually stopping to ask for directions.
You also highlighted another story about a patient that had a stroke in her right parietal lobe, and then you described this alien hand syndrome. She wanted to pick up a tissue with her left hand, and she couldn't make it happen. What's going on there?
Yes. Actually, so the video is online, and it's really dramatic and quite stark and really, upsetting to watch. She's trying so hard to do such a basic thing with her hand. She's in her later years, she's spent all of her life being able to say, I want my hand to do X, and my hand will do X. And because of this stroke, she found that not only was it not doing what she wanted, but it was doing other stuff that wasn't what she wanted it to do. The damage in her brain, it was in a part of the brain that's very important for representing location, so spatial information, and it helps us to keep track of where the salient things in our environment are relative to our bodies so that we can then act upon them. On one side of her body, that spatial map was knocked out. Effectively, the arm that would normally be getting direction from that spatial map via the motor cortex effectively was getting information from the wrong hand, looked for other places for information.
Yeah, the reason I wanted to highlight that is the stroke wasn't in what you would call the motor cortex. It was around it, behind it. But that's how this map is so complex, right? I mean, it's another area, not the motor cortex, but it was really futzing up her hand motion.
Yeah, absolutely. And kind of what it reveals is that there's not just one map that we use for anything, including vision or movement or spatial representation. We have many different maps in the brain, and the information passes between these maps. We often have this sort of transformation of information from what we see to what we represent to what we then act upon. Disruption to these different maps can create very different problems in people who are dealing with the consequences of stroke.
I think that sight, smell, taste, and our perception of them is incredible. So then what is the difference between imagining an image and seeing an image?
I love this question. I love thinking about mental imagery because I feel like it's one of those things that, that would be one of the hardest nuts to crack in terms of neuroscience. What even would be mental imagery? But what's amazing is that you can actually see mental imagery with a brain scan. You can see what people are imagining to some degree based on their brain maps and the activation. So when you imagine something, you generate activation in these maps that is similar to, but a weaker version of the activity you'd see if they were seeing or feeling the thing. And that's kind of remarkable. And I think it kind of blows my mind to this day that you can give someone a brain scan and tell when they're imagining a face versus when they're imagining a house. You can actually see differences in activity, that it's so similar.
I want to take it to the even more difficult thing to explain. How do we grasp inanimate objects? Like you use in your book the examples of debt, love, and compound interest. How does a brain map account for that?
Yeah. It's a question that we're still disentangling, and it certainly doesn't come down all the way to brain maps. But there is evidence that we use our brain maps to help us with understanding these ideas. even though brain maps, as I said, are representing very concrete physical things. And so by nature, you would think that we wouldn't use them to help us understand. But we actually tend to create analogies. And we use those analogies to help us harness our brain maps to think about things that are very much not in the here and now, not physical, and very complex. You know, it helps explain why we understand concepts much better when we can see a picture of them. Why is it easier to understand complex data when you see a graph of it than when you just see the numbers?
Yep.
Because we can use the physical spatial relationships between things, and we can very easily extrapolate that to something more abstract.
Hopefully we can agree that we'll never understand the concept of love, but is it true that, like with debt and compound interest and time, you can at least then start thinking about it in a numerical fashion, which gives it an image and some graph, as you said, that you can somehow visualize and put it in perspective?
Yes, exactly. So being able to see it and engage with it in ways like that, in more concrete ways, makes it so that we can better understand the relationships and then make good judgments about, for example, saving for retirement once we can visualize our financial situation.
You also get into the brain-computer interface and the sci-fi stuff about mind reading. Please disavow the people listening to this that somebody's not going to be able to read my mind tomorrow.
Yes, we are not going to be plunged into the matrix. And I think there are things to be concerned about with brain-computer interfaces, but I think that what happens is people don't know enough about it to know what is concerning and what is not. So what we're definitely not going to do is be able to read all your thoughts and know what you're thinking and implant complex thoughts and backstories into your brain. But when it comes to reading out more basic things, like what you might be seeing or what you could be imagining on a very broad scale, like is it a face or a house, not, whose face is it?
Well, you talked about Carol that was struck by a car and was in a vegetative state, and you put her in a functional MRI scan. Maybe you could use that as an example.
Yes, absolutely. So Dr. Adrienne Owen and others have been using these properties of the brain, that when you imagine something, you activate these areas that we can reliably identify and localize, to try to discern whether patients who are in a vegetative state are in fact conscious. Which is a long-standing question and incredibly important if you think about their well-being. Knowing whether or not they're conscious makes a huge difference. So he put people who were in a vegetative state in an MRI machine, and he did functional MRI, which can detect changes in blood flow in a way that helps us know what parts of the brain are more active. So he would say, if you can hear me, I want you to now imagine that you're playing tennis, and I want you to now imagine that you're walking around your house. This would activate a part of your motor cortex for the former, and for the latter, it would activate a part of your brain that represents locations in space. So then he would ask questions like, if your mom is named X, imagine you're playing tennis. And there was a surprisingly large percentage of them who could, on command, create that brain activation, demonstrating that they were conscious. So it really became a bridge between him and the patient.
This all sounds fantastic. Be honest with me. What's the downside to brain maps?
What is the downside? Well, actually, I think the downside to brain maps is that they both enable us, but they limit us. Because what we don't have mapped, we are very hard-pressed to even imagine. For example, you don't dream or imagine seeing out of the back of your head, or this is sort of the canvas upon which your perception is painted. And all else, other perceptions, the sensory experiences of other creatures, etc., we just don't have access. We don't even have the architecture to really imagine what that would be like other than by analogy. It's like we're enabled by these maps, but we're also constrained because it's what we got.
Yeah. The cards you were dealt.
Yes.
You said it yourself. How should this book change the way I experience the world around me? What was your goal regarding understanding brain function and the purpose of this book?
Yes. So what I was struck by when I talked to the public is that most people who are not neuroscientists, don't know about brain maps. They think it sounds like crazy. So really being able to explain what it is and present the beauty of it and also kind of the explanatory power of it, that this is why you are the way you are. This is the physical features of your brain that make you think the way you do.
It's easier to think about the heart, the liver, the kidneys. I mean, they have a specific function, but the brain is your mind, your soul, your being, and it's so difficult to explain. And I think you achieved that. Rebecca Schwarzlose, thank you so much for spending this time with us and describing brainscapes and, more importantly, what brain maps are and how important they are in terms of our perception of the world. Most importantly, making that whole concept understandable to us. Thank you so much for being with us.
Oh, thank you. It was such a pleasure.
This is Your Brain with Dr. Phil Steig is produced for the Weill Cornell Brain and Spine Center by the Really Interesting Picture Company. The episode producers are Geraldine Abinader and Hildy Rubin. The series is directed and edited by Tom Beltry, with music by Lenny Williams of Load Bearing Music. The announcer is Allison Power. Please contact us at drphilsteig.com or follow us on Facebook at This Is Your Brain. The writing of Brainscapes was supported with a grant from the Public Understanding of Science and Technology program of the Alfred P. Sloan Foundation.